so let's continue our class. In previous class, we discussed about how to quantitatively describe the flow process. Then probably you will say, oh, we can use the flux of entity, physical entities, including the heat flux, mass atomic flux, or electrical current, or electrical flux. And the unit for the flux actually is numbers of physical entities passing through a specific area and during the time period. Then next, you have observed the flux, so definitely there's driving force apply on your system or your materials. So if you observe the mass transport, then definitely the presence or exist of the chemical potential gradient. And if you can observe the heat flow passing through your materials, so definitely a temperature gradient. And if you can observe the electrical flow, which means the current passing through your materials, so there's a electrical potential apply on your materials. So we have a driving force, and each driving force will drive the corresponding, directly drive the corresponding flux. And regarding to now we know the driving force and corresponding flux, then regarding to the inertia of the system, which is more related with the material properties. Some people call it will be the transport resistance or mobilities. So let's take it for example, if we talk about the diffusion stuff, atomic transport happen in your materials, then the inertia of system will be which material property will be the diffusivity of these materials, right? Because if the materials has different diffusivities, then the mass transport, definitely the velocity of mass transport definitely different, right? Even though there's a same amount or magnitude of the driving force applied on these materials. If we talk about the heat flux, so the inertia of a system or transport resistance will be the thermal conductivity of these materials. If we talk about the electrical flow, then the conductivity of these materials definitely will affect this flux. Okay, so actually we already show you this universal equation can correlate these parameters to quantitatively describe the flow process in kinetics. And we also emphasize none of the energy state functions is best to describe this flow process. So the reason for that is, like we say, in order to determine the Gibbs free energy, the change rate in Gibbs free energy, you need to sum up all these three terms. So you can see that it's a negative term, positive term. So you need to figure out each of them and sum them up. So this is a little bit complicated to understand or determine dg over dt, the value of dg over dt. So here we would suggest the entropy probably would be the better choice or best choice to describe the flow process. Why? As you know, the flow process actually is an irreversible process, right? And in the irreversible process, we know the entropy always larger than zero, so always positive. So in this case, so we can use the entropy change rate probably to describe the flow process. If this flow process happen fast, then the entropy, the change rate or entropy production rate definitely larger, right? Okay, so here we demonstrate and show you the universal equation, which is the absolute temperature times the entropy production rate prevalent equals to the flux times the corresponding the flux and the driving forces applied on these systems. So in order to demonstrate this universal equation is really can well quantitatively describe the flow process. So we are going to spend like several slides to demonstrate three flow process to show that this equation can be used in three flow process. Included the first one will be the heat flow process, and the second one will be electrical flow process, and the third one will be the mass transport flow process. So let's move to the first one. The first one is the heat flow process. So the title here will be the entropy production in the heat flow process. So what we have here is we have two chambers with different temperature T1 and T2. And as we know, T1 is larger than T2, so we have a hot chamber and a cold chamber here. And we use the metal bar to connect these two chambers. So as you know, T1 is larger than T2, so that's definitely a heat. Delta Q flow from chamber 1 toward to chamber 2, right? Okay, so in order to know the entropy production in these whole systems, so the first, in order to know that, so you need to calculate the entropy change, right? So which laws will come out from your mind? That will be the second law, in the thermodynamics, right? So in the second law, it tells you the change, the entropy change in chamber 1 can equals to what? Because there's a heat flow out, right? So you got the minus dq because the q is flow out of the chamber 1. So we got the minus dq divided by temperature T1. And for the chamber 2, actually the chamber 2 will get some heat from the chamber 1. So you got the plus turn dq. So T1 lose some heat and the chamber 1 lose some heat and the chamber 2 get some heat. Okay, then in this case, we're divided by the temperature here is a T2. So in order to consider the net entropy change in these systems, including the chamber 1 and chamber 2, so we will write it down, the entropy change in total, or some people will call it the net change in entropy equals to ds1 plus ds2, this term plus this term. So after arrangement, what we have is we get this term. And as you know, T1, T2 is at absolute temperature is much larger than 0, it will be positive term. And dq actually here is a positive also. And the upper portion is T1 minus T2. T1 is larger than T2, so we got a positive term here. So positive, positive, positive. So the net change in entropy must be positive, right? So this result tell you what? This result tell you the heat flow will generate the entropy, or you can call it, will lead the entropy production. Okay, so in this case, we know the heat flow will cause the entropy production. But don't forget, the purpose here actually is we want to show you the entropy production rate prevalent, right? So what we have here, we only have a net change in entropy. There's nothing related to with the time and also the violent term, right? So what we are going to do is we are going to convert it or get the entropy production rate prevalent here. So Before that, we need to name something in order to determine the valence here. So there's a metal bar connect these two chambers, right? So we assume the cross-section area of this metal bar is A. This area is A, and the length of the metal bar is L. So we can simply formulate the entropy production rate per valence. Use a ds net divided by the time period delta t and the valence A times L. And we just put this term inside here, so we got this one. This part actually is a ds net divided by T, A, and L. And after arrangement, so how to arrange these several terms? We want to link the entropy production rate with what? With the flux and the driving force. So in this heat flow process, what's the flux here? Would be the heat flux, right? So we put the heat flux here. Heat flux will be what? ds is a heat. Flux means the unit time period and unit area. So we put this term here. And the rest of them, I put a T1, T2 here. And the driving force here definitely is related to temperature gradient. So the rest of term actually is a gradient term, right? It's T1 minus T2 divided by L. Is the rest of term here is a gradient term. Why is gradient? Is a delta T. It's a difference in temperature divided by the length, which we call a gradient term. Okay, so now what we have is this is a heat flux times the 1 divided by T1, T2. In order to make the things simple, so I make a assumption, which is the T1 plus times T2 equals to Tm squared. This means I assume that there's no big difference in T1 and T2. T1 almost equals to T2, so I can make these assumptions. In order to this one, so T1 and T2, we will use the Tm squared to substitute it. Then I put a 1 Tm here and the other Tm here. And this T1 minus T2 divided by L, I will put a temperature gradient term here. And it's T1 minus T2, right? And heat flux is passing through this one. Usually, in most of cases, the flux is here from here to here. So we usually, the gradient term, usually we use the ended point minus the start point. So it will be the T2 minus T1 will be divided by L will be the gradient term. So here I will got the minus temperature gradient here. Okay, so now we got the flux and what? And this 1 divided by Tm and the gradient term divided by Tm, right? So next, don't forget the left term is entropy production rate per valence. So the universal equation actually you need to times the absolute temperature. So Tm is going to move to the left-handed side. So we are going to get this one. Absolute temperature times the entropy production rate per valence equals to heat flux times the extra term. So this extra term we call it is a driving force to drive the heat flow in heat flow process. So this is so we successfully to demonstrate that in the heat flow process, we also can successfully derive these universal equations, which is the absolute temperature times the entropy production rate equals to flux times the driving force here. But please be attention here. Some people probably will think about professor driving force, but here the driving force actually in this case is minus temperature gradient divided by temperature. The unit probably is not the force which we learned before, right? So I will say this is a result from series deviation. So this is definitely, you can consider this is a driving force to drive the heat flux. But yes, the unit is not the the unit of force we learned before, but this is a special case. But after several slides after that, I will show you, after you check the unit part, uh, for the unit is, if you check every unit, for example, like you check this unit, this times this, and the unit will be the same with this one. So although this unit is not a general unit for the force, but in the heat flow process, this also can be considered as the driving force. So afterwards, if we talk about the heat flow process, this will be the heat flux, and which force drive this heat flux will be the minus temperature gradient divided by T. Okay, so this is the first case, heat flow process, and we successfully demonstrate the universal equation works in heat flow process. So next, I'm going to show you the second example is the entropy production in electrical flow process. And the purpose here also, we want to demonstrate that universal equation is also work here, and also define what is the driving force in electrical flow process. So what we have here is we have a yellow metal bar, and this metal bar with the resistance R, cross-section area A, and also the length L. And we apply an electrical potential across or at two ends of this material. It's V1 and V2. And as you know, and here V1 is larger than V2, so we got the current, electrical current Ch1 passing through these metal materials. And as you know, as long as there's a current passing through a resistance, a materials with resistance, then there's a very famous effect or phenomena, right? Which we call the Joule heating. That means as long as there's a current passing through this resistance, then they will generate the heat, which we call the Joule heating. And the power generation rate, P, can be equals to I squared R, right? Okay, and because it generates some heat, so you can write this down as dq over dt, or delta q over delta t means there's a heat produced from these materials, right? Okay, so based on this, as you know, there's a power generated from this phenomena, a heat or power generating from this phenomena, and we are going to write down based on the Ohm's law the power generation rate per univalent. So we need to put the per univalent here because we don't forget our purpose is to correlate the entropy production rate per valent with the flux and driving force, right? So here we are going to, so we write down the heat generate rate or power generate rate per valent. A times L is a valent, and can be, this is P, right? So it's I squared R. Then next, I'm going to put left one I here, and the rest of part is IR, right? IR is the V, right? The difference between V, right? So it's a V1 minus V2. And I put one A here, the other L here. Why I want to arrange them in like this? Because I want to correlate this with the current density is a current electrical flux, right? And this turn out is what the difference of the electrical potential gradient, then you divide it by the length, so it's the electrical potential gradient, right? So here, so you can write it down is like the current density times the electrical potential gradient minus electrical potential gradient. So in this case, we will get the current density times this one actually is the driving force in the electrical flow process. Okay. And it's a minus electrical potential gradient, usually because the current passing through this direction. So we usually use the V2 minus V1 divided by L as a gradient term. And V2 minus V1 divided by L is gradient of electrical potential, right? But this is V1 minus V2, so we need to put the minus here. Okay, so now, actually, the power or heat generation rate per univalent can express like this, but they also can express like this way. Just move the valent part to the upper portion. And what's this? Delta Q. What's the change of the heat? You can write down T delta S, right? So we call T delta S. Okay, so now you got the entropy term, right? Okay. So what's this term? Actually, it's the entropy production rate per valent. So this term can be equals to absolute temperature times the entropy production rate. And both these are the same, so this equals to this. So what we got is the absolute temperature times the entropy production rate per valent will be equals to current density times the minus electrical potential gradient. So in this case, we demonstrate that the electrical flow will lead the entropy production, or you can say that electrical flow will cause the entropy production. And in this case, we also show you that in the electrical flow process, the flux part will be the current density, and the driving force will be the minus electrical potential gradient. Okay? Okay, so what we have is we also have the mass transport or mass flow process, right? So that will be our third case, right? But before we move to that, we still have, well, I'm going to introduce or give you a quick review between what's the relationship between the chemical potential mu and the composition X. This is quite important before we talk about the mass transport stuff or diffusion in solid materials. So why? Because as you know, the driving force for mass transport actually is the chemical potential gradient, right? So you need to know or understand how to formulate the chemical potential of specific atoms at specific composition. Otherwise, you don't know the gradient, right? The difference in chemical potential of the atoms, right? So let's take an example here. Now we consider we have AB alloy with the composition XA at constant temperature and pressure. At constant temperature and pressure, this tells you what? The change of Gibbs energy totally contribute from the composition change, because now we have the constant temperature and pressure. Okay, so let's formulate the total Gibbs energy of AB alloy. So you will write down the numbers of atoms A times the mu A, the chemical potential of atom A, plus the numbers of atom B times the chemical potential of atom B, right? And next, probably we'll formulate this one will be equals to numbers of atom A times the mu A0. Actually, is the chemical potential of atom A in the pure A materials, plus NB times the numbers of atom B times the chemical potential of atom B in pure B materials. This is a pure A part plus a pure B part, and because this is alloy, so you need to minus the mixture entropy, mixture term, which will decrease the total Gibbs free energy, right? So the mixed term will be used minus T delta S mixture. And based on statistical thermodynamics, you know the entropy, the mixed term in entropy can be equals to the Boltzmann constant K times the log omega. Omega here is the numbers of possible states of the systems. So be the combination between the A and B. So we will rewrite them as like this: K times the NA plus NB factorial divided by the NA factorial and the NB factorial. And we assume the NA and NB numbers of atom A and B is very large, so we can do this approximation here. Next, we substitute this term inside here, so we can rewrite the Gibbs free energy of atom AB alloy like this. Okay, so next, my question, back to our questions. Can you write down the chemical potential of atom A at specific composition of XA, at XA? So, do you remember what's the definition for mu A, chemical potential of atom A? Actually, the definition is when I added 1 mole of atom A, how much the total Gibbs free energy changed in our systems, right? So we directly use this term and divided by the NA, the partial with NA. So you will get this term mu A0. This we don't have NA, and also this term will be KT log XA. So you got this results. So this is quite important. So mu A, chemical of potential of atom A x XA composition equals to mu A0 means the chemical potential of atom A in pure materials plus the KT log XA, which means what? Which means tell you that in the alloy part, as you increase atomic fraction of atom A, then the chemical potential of atom A increase in the meantime. So you add the composition of A. If there's more A in our alloy, then the chemical potential of atom A actually is higher at that moment. Okay, so this is very important part, right? We can write down. This is the relationship between the mu A and XA. And we also can use this term and divide it partial with the NA, so you will get this result. So it's a mu A0 minus TSA bar. And SA bar actually people call it as a partial atomic entropy. And compared with this term, you know the partial atomic entropy actually expressed can be equals to minus K log XA. So what's the partial atomic entropy? Actually, the meanings or definition is a little bit similar with that in chemical potential of atom A. Is when you added 1 mole of atom A, the total entropy change of the system. We call it partial atomic entropy. Okay, so in this case, we make a short summary here. When you increase the atomic fraction of atom A, then the partial atomic entropy will decrease, but the chemical potential of atom A at XA per composition will increase. So now you can formulate, no matter at what kind of composition of A10A, you can formulate its chemical potential, right? So let's move to the third case, which is the entropy production in mass flow process. So what we have here is we have AB alloy, and there's a composition difference at two ends of this alloy or these materials. At your left-handed side, what we have is we have XA1, and your right-handed side we have XA2, and the cross-section of these materials is A, and the length is L, and we know XA1 atomic or fraction of A10A1 is larger or higher than XA2. So as we know, there's definitely an atomic flux passing from 1 to 2. Ja is from 1 to 2. Okay, so as you know, what is the driving force to drive this mass transport? It's not the concentration gradient, right? It's a chemical potential gradient. So the chemical potential difference between 2 and 1 actually, you can use the mu A x2 A2 minus mu A x A1. So we need to formulate what is the mu A x A2. So based on previous slide, we know mu A x A2 can be equals to mu A0 plus KT log XA2, right? And mu A x A1 will equals to mu A0 plus KT log XA1. So use this term to minus this one, so you got the KT log XA2 minus log XA1. And if you use the entropy part, then you will get the minus T delta SA bar, right? And based on this, you know XA2 is smaller than XA1, right? So this will be the negative. And this will be a negative as well. And based on this, you know the change in partial atomic entropy is positive. Okay? So next, we try to correlate this with flux, atomic flux and driving force. So also the entropy production rate. So what we have here is we want to know the heat, total heat passing through these materials. So we got the T delta S is a dq, right? And this is only one. This heat actually is related to one atom A. So we plus the changes in of atom A, it will be the total changes in heat, and we use divided by the time and also the volume of the system. So T delta S is dq, right? And also you compare this, actually is a minus chemical potential difference. So we put a minus potential difference here, and the rest of part are the same. And also what we have here is we just make the arrangement here. In order to formulate the flux, we know the flux is atomic flux will be the delta Na, numbers of atoms per unit area per time. So we put this and the rest of part here. So you can write down the atomic flux. This is atomic flux times the minus chemical potential gradient. Okay, this is a difference. Delta mu divided by L is a gradient, and minus electric or chemical potential gradient. And now we have the flux and driving force, but the left turn, is it related to entropy production rate? Yes, what you have is a UST, right? This is a temperature times the entropy production rate per volume. So the left term actually is a temperature. This is the the partial atomic entropy times the numbers of changes will be the total entropy change, right? So it's a T. So this is a total entropy change per time per valent, and this is a temperature. Okay, so we successfully to demonstrate the universal equation can be also work in mass flow process, and in this case, the flux is atomic flux, and the driving force will be the minus chemical potential gradient. And some people probably will consider how to get this. Why in the beginning you can formulate this term. Probably you will think about you just formulate the temperature times the entropy production rate per valent. So entropy production rate here is total entropy produced from this mass flow process, right? We only know the partial atomic change, then we times the total changes in numbers of atom A, and you divide it by time and valence. Okay, so this result demonstrates that the mass transport or the atomic transport will lead the entropy production. Okay, so now I give you a short summary here related to the entropy production and the flow process. The rate of entropy change instead of free energy change has been used to characterize the irreversible flow process. And we already show you that the heat flow, electrical flow, and mass transport can lead the production of entropy in the system. And we also get this universal equations which can quantitatively describe how fast this flow process is by the use of absolute temperature times the entropy production rate per valent equals to the flux times the driving force. And I just summarize some results here, and you can check the results shown in previous slide.